Hi, Prob Stats, and welcome to 6.4. I hope you did well in the 6.3 reading. And this is the central limit theorem. And this here only works when n is greater than 30. So we got to have a large sample size. And it shows us how everything kind of goes together. I hope you enjoy it. It's not actually too bad. All right, so the goals here, we want to describe the central limit theorem, like what it does. We want to apply the central limit theorem by finding the probability and the sample mean, and identify the conditions that are appropriate so we can use this central limit theorem. Now, the central limit theorem, the same size n, okay, so for all samples of the same size n, so out of our population, and n has to be greater than 30, say I'm going to pick 40. I would have to have 10 or 20 or 30 different samples, but they would all be of 40 things. That's what that means. The sample distribution of x bar, so your mean, can be approximated by a normal distribution with a mean and a standard deviation of the standard deviation, but divided by the square root of n. This is how I find our mean. So it's a little new formula. It's not too bad. Whoops. Let's go back up here. Okay, population has a mean mu and a standard deviation of sigma. The sample, all of size n, are selected from the population, so they all have the same size. Simple random samples, all of size n, they have to be identical. So if I pick 35 people, every single thing we look at has to have 35 people. It cannot change. That sample size is very important. Okay, the requirements, n has to be greater than 30. All right, the mean is represented by x bar. So this is the mean of our samples is mu. The standard deviation of x bar is the standard deviation subscript of x bar is the standard deviation divided by the square root of how many we have. And then z is very close again. Now it's x bar minus the mean divided by the standard deviation divided by the square root of n, which was how we found the standard deviation for our population. All right, here we go. We have to check requirements. Sorry. They have to be normally distributed, and n has to be greater than 30. Very important. Okay, if it's an individual value, nothing different. Z equals x minus mu over the standard deviation. The mean from a sample of values. So we've done a bunch of them. So remember now we have sigma over the square root of n for the standard deviation. So now when we have z, we have our average value, our mean, minus our population mean over sigma divided by the square root of n. A little bit different because we have a lot of them to do. Here's an example. Okay, we want to know if our elevator is safe, like will people die? In the airport, it says there's a maximum capacity of 4,000 pounds, which is 27 passengers. I want to know if there's a mean passenger weight of 148 pounds when the elevator is full. That's what, so if we take 4,000 divided by 27, we get 148. Okay, worst case scenario, I have 27 adult males. Okay, a male has a mean of 189 pounds and a standard deviation of 39 pounds. We want to find two things. The first one, the probability that just one of them is greater than 148. And the second thing I want to know, the probability that the sample of 27 has a mean greater than 148. So what happens when one? What happens when all of them is what we're looking for here. I'm back. All right, so we're going to start with A. Okay, this is a single individual. All right, we're dealing with just one guy. We want to know if one guy is the average that I can pick one of them and he'll be over 148 pounds. So I know my mean's 189, right? His value is 148, and I want to know that one of these what's the probability that it's greater than? So it's all to the right. So your first step is we have to find our z-score. So it's 148 minus 189. We get a negative 1.05. Plug that into StatDisk, and you're going to get 0.1469. Remember, you're looking at the right side. Okay? Sorry, that's if you looked at the left side. You could look directly at the right side and it would give you the answer, a 0.8531. If you're using your A table, you will have to subtract from 1. I should not have put that in there. Okay, so you got 0.85. So there's an 85% chance that if I pick one guy, he's going to be over 148 pounds. All right, this is not looking good when we have 27 guys. All right, so now what's the probability that this elevator is going to crash if I have 27 adult males? So now we use our normal distribution and the information we're given. So we know that the average of the x-bar is equal to the average, which is equal to 189. That stays. Now, my standard deviation is that 39 pounds divided by the square root of 27. When we calculate that out, we get 7.50555. All right, which rounds to 7.51. Now I've got to calculate my z-score. So that's x, the value I'm looking for, 148, right? Minus my average, which is 189, and over the 7.51, which is my standard deviation for this many people. When you type that in, you're going to get a negative 5.45939. All right, if we use StatDisk to find the area to the right, it's actually going to tell you 100%. All right. Now, the problem with this is that we know that this last part on a standard deviation curve, remember this? We said all of these get grouped together. All right, when our numbers get so large, we're going to assume that all of this area right here is going to be 0.0001. So anything when it's negative 0.5 and it gives you a 0, we're going to plug in 0.0001. So we're going to have a 0.9999 area to the right of this thing, which means 99.99% chance that this elevator will be overweight if filled with 27 adult males. So it's going to crash. This is bad. All right, now it's your turn to try. Oh, I forgot. Okay, I'm recording this before you've actually done your data, so you're going to have to do this on your own and post questions. After I have the data, I'll put the questions online. You create a data plot from the x-axis, and we want to represent the central limit theorem. So you're going to put all your data here. You're going to find the mean and redo that. And what that should show you is that this mean is the same as the mean of the population, which is where we're going. All right, good luck. Okay, hypothesis testing. Okay, this is the rare event rule. If under a rare event rule is what we're talking about for inferential statistics, we want to know if it's significantly less than or significantly greater than. So that's more than 2 standard deviations from the mean again. Now, let's show you what this does. I'm going to assume that the population of the human body has a temperature of 98.6, right? That's what we all had to do with COVID. If you were at this or in a certain range, then you could go into places you weren't sick. Assume the population standard deviation is 0.62. So my standard deviation is 0.62. That's what they said from Maryland. They did a research. Now, a sample of 106 people, randomly selected, find the probability of getting a mean of 98.2 or lower is what we're looking for. So I know my population mean is 98.6. My standard deviation is a 0.62 divided by the square root of 106, the 0.0602197. My z-score, 98.2. I want to see if this is more accurate than the 98.6 divided by my standard deviation. Are we doing good so far? And we get, when you actually type that in, my z-score is a negative 6.64. Now remember, this is in that lower tail, so we're going to use that 0.0001 because it's going to show 0, and we're going to use this. Okay, the results show that the mean of our body temperature is really 98.6, as we assume when there's extremely small probability of getting a sample mean of 98.2. Okay, so the population temperature is what it says, 98.6. That's the first case that this is what's true. Or the population mean is actually lower than the assumed value, and so their sample is typical. Probably not true. They probably just can't measure. This is ridiculous. This is the true population. I hope you did okay with that. That's actually kind of fun. All right, it's now homework time. Post any questions if you have any, and good luck.